Hey guys, so hopefully yesterday's lesson went okay and you were able to follow. And if you have any questions, always remember just send me an email and I'll help you guys out. I'll figure it out for you guys. So today we're going to move on to chi-square test for goodness of fit, but this time we're going to learn how to actually do it in the calculator, which actually saves you a ton of time because all that work that we have when you have to find the chi-square test statistic, it's done instantly. So it'll save us a ton of time. Now, a couple things about the homework tonight, and I will post the file with the homework all spaced out nicely so you could fill it in. Matt Raffini once told me that sometimes the homework is a little long, and I kind of am going to try to keep it shorter now that we're doing online learning. So obviously not 3 because we did that already. Let's cross out 11, and 19 to 21 are multiple choice. So it shouldn't be that bad. Number 7 is a question why something shouldn't be chi-square. They give you a situation. And then number 9 is actually doing a chi-square test. So this one will be a little lengthy, number 9. And then 19 to 21 should be okay. So chi-square test for goodness of fit. Remember, chi-square test for goodness of fit, yesterday we talked about, is if you have a single categorical variable. So I always like to think back to a certain problem to remember what it was. So I think of that M&M's problem. Color was the categorical variable, and then we check to see if it matched up. So before we do that, before we do a chi-square test, we have to check for 3 different conditions. Condition 1, we have to check that the data comes from an SRS or random assignment if it's an experiment. We have to check that 10n is less than n, the population. Remember, that will tell us if the data is independent. And our third condition, we're not assessing normality because we're not using a normal curve anymore. We're not using a t-distribution. We're using a chi-square distribution. So we have this new condition for chi-square, and that is that all expected counts are greater than or equal to 5. That's expected. Now, how do you show that? Well, like yesterday when we made that table, you're going to make that table again and show what all the expected counts are. So just some things to remember. Before we start using goodness of fit, we have 2 important things to look for. The chi-square test statistic compares observed and expected counts. Don't try to perform calculations with the observed and expected proportions in each category. We need counts. It's a number of times something happens, not the percentage of times something happens. So there has to be whole numbers in your table when you're doing observed and expected. The percentages just tell us and help us to figure out the expected counts. And then when checking the large counts condition, that's the greater than or equal to 5, make sure you're using the expected counts, not the observed counts. Not what you got in the study or when you measured it, it's what the expected counts are. They all have to be, remember, greater than or equal to 5. Okay, so just a recap of what the chi-square test for goodness of fit looks like. If conditions are met to determine whether a categorical variable has a specified distribution in the population of interest, we use the following hypotheses. Null, assume that whatever distribution they state is correct, and then alternatively, what we're looking for evidence for, remember we're trying to reject the null and find evidence for the alternative, that whatever distribution was stated is not correct. We get our chi-square test statistic by doing the sum of the observed minus the expected squared over the expected. We did that yesterday by hand. Today we won't have to. Well, we will one more time, but then we won't have to. And you have k different categories, so the degrees of freedom is k minus 1. Number of categories minus 1. Now, one thing, and you're actually going to see this in the homework tonight, instead of writing your null and alternative like this, sometimes you'll see the null. Assume that P1 does equal whatever proportion they say it's going to be, and P2 does equal that, and P3 and P4, and all the way to P sub k. Now, this is a lot harder to write and a lot more annoying, so you see I will never write it like this really, but you could see it that way. And the one you see in the homework will kind of make sense. So here we go. This is one of my favorite problems of the year because it kind of makes sense. So it says, in his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on the chance to make the highest levels of the game. Specifically, because January 1st is the cutoff date for youth leagues in Canada, players born in January will be competing against players up to 12 months younger. So if you're born in January and you're born in December, you're playing in the same year, but you're going to be almost a full year older than that person. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, judged by whether or not a player makes it to the NHL, so that's what success is deemed here. A random sample of 80 NHL players from a recent season was selected, so they picked 80 players at random and X and when their birthday was. And the table below puts them into 4 different groups. So out of the 80 people, you had 32 born January to March, 20 born April to June, 16 July to September, and 12 October to December. Now, for expected, let's talk about expected. So first off, that's a total of 80. They told us that. So the expected, well, let's say nothing was going on. Assume nothing is going on. Well, if nothing's going on, and since all of these time periods are the same length, 3 months, 3 months, 3 months, 3 months, you would expect, well, 20, 20, 20, 20. That is what is expected. And once you write that down, you can immediately see that it looks like those born later in the year are less likely to be in the NHL, those born in the beginning of the year more likely to be in the NHL. So the question they ask, and here you go, this is your key that this is a significance test, is do these data, or does the data, we know, this is annoying, provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? So we're going to go ahead and do a significance test. And it's going to be a lot of writing, and we know that, so just bear with me. So first up, we need our hypotheses, right? For all you people who like phantoms, need your hypotheses. Now, you don't really need parameters because we're using a sentence here. So your null hypothesis, let's assume the birthdays of NHL players is, and this is the first time I think we've done one of these, evenly distributed. Because assume nothing's going on means that it should be evenly distributed. And alternatively, we're looking for evidence that the birthdays of NHL players are not evenly distributed. Okay, so we go ahead and we check our conditions, and to save time, I'm not going to write them. You guys are good at that by now, right? Data comes from a random sample. Yes, it tells us that. 10 times 80 is 800. Is that less than all NHL players? It is. It actually is, especially since it doesn't say it has to be current. It's just all NHL players, which, yeah, that's true. And then are all expected counts at least 5? Yes, 20, 20, 20, 20. And I already showed that, so when I would state that, I would just show, I would say C expected column. And there it is. Okay, so now what do we have here? We can name this. It's a chi-square test for goodness of fit. Okay, with degrees of freedom equal to 3. 4 minus 1. 4 categories minus 1. Okay, at alpha equals, does it tell us? No, but let's make it 0.05. So there we go. There's our name. We have named the test. Now, I have to get the chi-square test statistic next to be able to use chi-square CDF to calculate the p-value. So we know I'm going to do that down here. Chi-square equals the sum of the observed minus expected squared over expected. So let's do that. This can be a little lengthy. So we get observed. This, let's do first January to March. So January to March. 32 minus 20 squared over 20 plus April and June. Okay, well, April and June, check it out. Observed and expected are 0. The difference is 0. They're the same. So when you do 0 divided by 20, 0 squared divided by 20, this is just going to come out to 0. So actually that saves us a lot of time. And then plus 16 minus 20 squared over 20 plus 12 minus 20 squared over 20. And we calculate this, and I already did the math. You get 7.2 plus 0 plus 0.8 plus 3.2, which gives us a chi-square test statistic of 11.2. Now, what does that mean in a picture? Well, our chi-square distribution, which is always in quad 1, we have to calculate the probability of being, should be skewed right, 11.2 or greater. Now, I don't know if this picture is accurate. I actually kind of royally screwed up, and the calculator I grabbed from school is not updated, so it does not give me the menus, so it kind of sucks. So until I get one, we're just going to have to rely on, I'll post a YouTube video on how to do it or something, and on the next screen I gave you pictures, so it should be okay. But chi-square CDF from 11.2 to 9999999, degrees of freedom 3. And now what information do we write down for our test? So we write down the chi-square test statistic, which is 11.2. And now our p-value, when I do the chi-square CDF, and I did it earlier, it came out to 0.0107. Okay, so what do? Well, p-value less than alpha, right? P-value less than alpha, reject the null, say we do have evidence that the birthdays are not evenly distributed. So that's basically what we're going to say now. I'm going to type this down here. I don't know why it does this, but whatever. Here we go. Since our p-value of 0.0107 is less than alpha equals 0.05, we reject the null. We do have evidence that birthdays of NHL players are not evenly distributed. There you go. So that is an example of a chi-square test for goodness of fit. And very similar to what we've done, that's good. And p-value less than alpha, regardless of what they're teaching you in bio, for all of you bio people. We just do it the same way we've been doing everything. If your p-value is less than alpha, reject, then I'll say you have evidence for the alternative. Right? How do we do it in the calculator? Well, it's actually not that bad. So for chi-square test goodness of fit, what you're going to do is this. It's in the test column, so stats tests, and then it's chi-square GOF test. Now, when you click that, it tells you observed and expected in degrees of freedom. Now, this color thing is if you have the new calculator, then it says calculate and draw. Now, notice that observed says L1 and expected says L2. What you're going to do in your calculator is you're going to go back and you're going to enter in the observed into list 1. So list 1 is going to be 32, 20, 16, and 12. And then what you're going to do is you're going to, into list 2, put all your expected counts. So 20, 20, 20, 20. That's all you have to do. List 1, observed. List 2, expected. And then your calculator knows to run the chi-square test. And you'll notice 11.2 is what we got for the chi-square distribution, and that's exactly what they gave us. And the p-value matches as well. Now, one thing I want to talk about is this column here that says CNTRB. What this means is contributions. It's basically telling us how much of the 11.2 is contributed by each section. So this 7.2, 11.2 is the full chi-square distribution. 7.2, as we remembered, was the part of chi-square from the months of January to March. And you see that makes sense because that was the largest difference from what we expected, so it's the largest contributor to tell us that something is going on, that we would reject the null. Same thing here. This one was pretty far as well, so that's why in October to December, we got 3.2. Now that's why the smallest was the one that had no difference, and then the next one that had the smallest difference was July to September, 0.8. So together it comes out to 11.2, but this column here is going to tell you the contributions for your chi-square test. Okay? just some things, right? And this is a good tip, as always. You can use the calculator to do all this. It's not a problem, okay? But there's a risk. So if you don't show your work and you get these numbers wrong, they're not going to give you the benefit of the doubt and say you made a calculator mistake. Instead, what they're going to think is you just don't know what you're doing. So how do we account for this when we're doing a test? Well, what I usually do, and this is good advice, is if you just show two calculations in chi-square, and then this part here that has the other work, you don't even need that really. I'm going to delete it for a second. You can put plus ... and show that you know what you're doing, but you're not going to be a clown and sit there and do it the entire time. So you can just show the first two calculations. Now, I wouldn't put 0. I would put 20 minus 20 squared over 20 and show it, and then put ... and then show the chi-square test distribution, chi-square test statistic. They'll give you almost all the credit, because then they're just going to assume, okay, this kid does know what they're doing. They just entered it wrong into the calculator, which happens. Okay, so that's my advice for that. Here's another problem. Same problem, actually. It's just showing you everything again. This is the contributions. We already talked about that. Cool. So what I want you guys to do is try the one on the homework. Try the homework problems out. If you have any questions, as always, send me an email. Or if you just want to say hi, it's cool too. But try it out and see how it goes. And yeah. All right, guys. Talk to you guys soon.